Okay, so let's do another problem here with Mathcad. So this is good because I think it's a problem that you might not think about doing in Mathcad because it's a statically indeterminate problem. So I'll show you how we can do it with this method of assumed forces. And actually, it's pretty easy to do. Like I said, I think I have some video solutions where we do like solving simultaneous equations in Mathematica, and that's not a bad way to do it. But actually, even though you don't have the ability to solve simultaneous equations in Mathcad, unless you have the full version, you can still use this method of assumed forces to solve these types of statically determined problems. And it's actually, I think, a very powerful method for solving a lot of different things. And so it's a good approach. All right. So again, we did this problem in class. I'm going to do the 431, the problem we did in class. Okay. Um, and so here, right, it's the concrete cylinder with eight 1-inch diameter rebars in it, and a 200 kip force, and figure out the stresses in the concrete and the steel. So here I've defined, I'll put the picture, I defined Young's modulus for the steel and for the concrete, and here's the length. So those are the things that we've done in class. Here are the diameters, right? I can also put these up here, I guess. The diameter of the steel, and then the outer radius. So, then we can easily calculate the diameter of all 8 steel reinforcement bars. Here's the area of the whole concrete form, and then obviously the area of the concrete is that pi r squared area minus the area of the steel, right? So there's the area of the steel, and there's the cross-sectional area that's concrete. All right. So again, we can do those calculations pretty easy. All right. So now, how do we solve this? Using assumed forces. So we know that the concrete and the steel have to deform the same amount. Their displacement has to be the same. Okay. I don't know what that is, but they have to be equal. So what I'm going to do is I'm going to put a unit force on the steel, and then a unit force on the concrete. See how much they displace. If they both happen to displace the same amount, most likely they won't, but let's say they do. Let's say they both displace the same amount with the same force, then that means that actually the load will be carried equally in both of those. The load in the concrete will equal the load in the steel. Okay? If, let's say the concrete displaces twice as much as the steel does for the same unit load, well, that means that there needs to be more force in the steel so that it compresses as much. So you have to have twice as much force in the steel. And that gets me the ratio of the force in the steel versus the force in the concrete. All right? So I'm going to say that again. So I'm going to use a unit force and then see how much both the steel and the concrete displace. That ratio is going to be the same as the ratio of the forces in the steel and the concrete to get them to displace the same amount. Okay? All right, so that's what I'm going to do. So here we go. We put in for the unit force, this big U is the unit force. So I'm going to use 1 kip just to make my life a little bit easier, right? So, and I put a negative here because it's compressive. All right, so 1 kip. And then the amount that the concrete will compress. So I use delta C, and I put a little I here because it's like an impulse. It's a unit. It's the force times the length over the area times C. So here's what I get, minus 2 to the minus 4th inches. And I can also do this for the steel, and it's minus 1.9. So it's a little bit less. So the steel does not displace as much as the concrete. So that means there's actually going to be, they have to displace the same, So if this concrete displaces more for the same force, that means we actually have to increase the force in the steel by that ratio to get them to displace the same amount. So here's that ratio. I'm just calling it S. So it's the ratio of the displacement of the concrete over the displacement of the steel for the same force. And in this particular problem, it comes out to be 1.071. So that means that the force that the steel needs to be that 1.071 times greater than the force in the concrete to get them to displace the same amount. Or in other words, you can write this as an equation, Fs equals S times Fc. All right. Oh, and I didn't think I did it in my intro thing. I should have. So you could also put in text in Mathcad, right? There's a little text box, and then you could type in whatever you wanted to do, right? You can change the font and all that stuff. So that's what I did here, right? So okay, so now we know Fs equals S times Fc. All right, and S is this 0.071. All right, so let's do this now. Okay, so we have, and again, I'm writing this out in Mathcad as a note. You can do this on a piece of paper, but I put it in a note so that you can see it. We know from the sum of forces that the force in the concrete plus the force in the steel has to equal to 200 kips. Okay? And now I'm going to just substitute in force in the steel is S times force in the concrete. So this is now equilibrium. Again, you would probably do this on a piece of paper. And now I can use this here to solve for the force in the concrete. And that's what's here, right? Again, because Mathcad can't solve equations algebraically, you have to type it in directly. You have to kind of do that in a piece of paper. But it's not that hard. So the force in the concrete is the 200 kips divided by S plus 1, right? Because you got a 1 here, and then an S, and here you pull out the FC, and that's what you get. So that gives me that the force in the concrete is 96.5, 96.6 kips, which is what we got in class. And then the force in the steel is going to be S times that, so that's 103 kips. So we got the forces in Mathcad. We don't have to solve systems of equations. We're using this assumed force method, right? And that sort of scaling argument. And now we've got the force in the concrete and the steel. Then I can figure out the stresses. So the stresses are just the forces divided by the area. And so here they are. They're calculating those, giving you those results in PSI. And if you want to really do a check, we can just do a check. Let's just check the displacements and make sure they're the same, right? So again, this would be something that you probably may not do on a homework because it's a little, it's extra calculation, but it's not so bad to do it here. So the displacement in the steel is the force in the steel times the length, times the length, all over the area of the steel times Young's modulus of the steel, right? And there it is in meters, but we want it in inches, right? And now let's calculate the displacement in the concrete, and they should be the same. I hope. If they're not, I'm going to just stop the video and redo it. And you'll never know. But I think it will be the same. Yeah, see, they come out to be the same. So you're good, right? This was the check. The check is good. All right, so a little different way of solving these things, but this assumed force method is actually a really powerful way to solve things. A lot of times we do that. And in Mathcad, you can also use this. I should make another video on this if we have a design problem. So for problem 432, they ask you to find the diameter of each rod so that 60% of the axial force is carried in the concrete. Well, I can do that really easy now. And I can do it without trying to juggle equations. Like, let's look at it right now. So right now, well, actually, the force ratio is right here. The force in the concrete is 1.071 times that of the steel. We want S to go to 0.6. All right, so what are we going to do? We have to well, actually, we want it to go to, well, no, I'm sorry, I should redo this. So the factor we want, I'll call it F, that's going to be equal to, well, actually, let's just do it more directly. I'm sorry, I'm talking too much. Let's just make sure we get it right. So the force in each rod, so that we want the force in the concrete to be 60% of the total force. Okay? So right here we got the force in the concrete. So that factor we want to check is the force in the concrete, oops, divided by the 200 kips. And you see now it's 48%. So we're at 48%. We want that to be 60. So what we want to do is reduce the diameter of the steel rods. They want you to change the diameter of the steel rods, right? Right. So we want more force in the concrete. We want the concrete to be stiffer. So we're going to drop the diameter of the steel rods. So we can just try, let's change it to 0.9 and see how much of an effect that has. All the numbers update, and we can scroll down. Okay, we moved up to 0.454, almost 0.6, but not quite there. So let's make it a little bit less. So we can do, probably 0.8 will be too much, but let's try 0.85. Oops. And almost 0.83. Okay, well, you get the idea, right? I can keep doing, maybe it's maybe 0.8 isn't that bad. Let's do 0.8. 0.8. Yeah, 0.8 is a little bit much, but it's pretty close. So 0.8 is about 60, so maybe it's 0.801, 05. I don't know. That's probably good. Yeah, all right, whatever. But you get the idea. So again, instead of focusing on trying to do the algebraic manipulation to get you the answer, which is what a lot of students struggle with on the exams and homework, it doesn't matter. We're just going to use Mathcad as an engine to allow us to figure out the answers that we need, right? And you don't have to worry about the algebra so much. We're using that as a tool to take the algebraic drudgery off of you, right? You can just do plug
It's
and
really
chug.
a dream
So you
come
can do a
true.
lot of
This
design
rover
problems in that way, okay? So again, really powerful, the assumed forces and the design approach, okay? So, all right.